Alright, so first part, intervals of increasing and decreasing behavior. I think before I get to that, if you take a look at your function, you want to be able to say what's the domain of your function. So that's going to play a role here in just a little bit, but the domain of that function, you've got a rational function, polynomial on the top, polynomial on the bottom. You can't divide by 0, so if x were to be 0, you'd be dividing by 0. X can't be 0, so my domain is negative infinity to 0, union with 0 to infinity. Be careful, like sometimes you'll get a function where like we can't divide by 0, but you're going to want to take a look further if 0 would have also made the numerator 0. But really the big thing you're looking for, x cannot be 0, so eliminate 0 from your domain. So now I would actually move into A, intervals of increasing and decreasing behavior. And like Karate said, in A you are going to need the derivative. So what do we got for the derivative? Anybody? Abby, what do you got?
It's 2x squared minus 9 divided by x2.
Okay. Alright, so your derivative is going to be what gives you instant access to whether your function is increasing or decreasing. So that's going to be what we use to examine whether the function increases or decreases. So if your derivative is positive, somewhere you're increasing. If it's negative, you're decreasing. Do we want to check that?
I think it's negative 18. Yeah. Because it's it's like 2 times x squared minus 9.
Oh, 2 times, so it sits like this.
Yeah.
Okay, perfect. Okay, awesome. So we're sitting with the derivative. Now we've got to go and look at our critical points, right? You really want to break this thing up. So I'm going to have different intervals, some of them increasing, some of them possibly decreasing. But as far as where I separate those intervals, the separators I use, critical points play a big role there. So critical points. So critical points. Well, we've been talking. We said, hey, that's where f prime of x is 0. F prime of x is undefined. And that's almost complete for critical points. There's one more thing, though. In order for x to be a critical point, f of x needs to exist. Right? And that's kind of something I left off. I just didn't want to give you too much at once. So you'll notice when you look at the derivative, is your derivative ever undefined? Yes, when x is 0. Now careful, remember to pull in this last qualification. Your derivative is undefined when x is 0. Does that mean you have a critical point at x equals 0?
Yes.
Look at what's in yellow. If you're going to call it a critical point, it's got to meet that yellow condition too. Does f of 0 exist?
Yes.
No, because you go back and you look at the domain. So since 0 isn't in your domain, f of 0 doesn't exist. Now 0 is important. It is one of those separators. It's not a separator, though, because it's a critical point.
Wait, so does that mean 0 is not a critical point?
0 is not a critical point. Are we going to use it as one of our interval separators? Yes, we have to. Like if your function goes from existing to not existing, then you're going to have to break up, your description of that function increasing or decreasing there as well. Right? So on the domain of the function, is f prime of x ever undefined? No, because 0 isn't in the domain of your function. But anyhow, first, now go to your derivative being 0. So if somebody wants to just grab their 89 and solve that, f prime of x equals 0 when x is plus or minus 3. So some students did that real quick without a calculator. You're just looking at the numerator. If you've got a rational function here, the only way to get 0 out of a fraction is 0 in the numerator, while 0 also doesn't make the denominator 0. So if x is 3, the numerator is 0, the denominator is not. if x is -3, the numerator is 0, the denominator is not. So f prime of x equals 0 when x is plus or minus 3. Okay. I want to leave this, I want to make note of this too. F prime of x does not equal undefined on negative infinity to 0, union 0 to infinity. This is kind of nitpicky, but you really want whoever reads this to know that you did care about when f prime was undefined. So you need to have evidence there that you checked it. And I think this is a really intelligent statement. Yeah, I checked it, and I was very specific to only check it on the interval where f is defined. So now we're going to set up the intervals. Okay, so we really have how many separators for these intervals? 3. Good. So you got -3. You have 3, and you also have 0. So our intervals, so we've really got negative infinity to -3, -3 to 0, 0 to 3, and 3 to infinity. So those are the intervals we care about. Now, is it possible that on 2 successive intervals, f will be increasing or f will be decreasing? Yeah, sometimes that'll happen. So just because they're separate doesn't mean that f will necessarily change from increasing to decreasing. But these are the only places where it could happen. Right? Those are the only spots where your function is going to be able to change from going up to going down or going down to going up. Alright, so now we have to make some intelligent statements about when is f increasing. Okay, so I'm going to go ahead and say, I'm going to say f is increasing on, so we're going to have to put in some intervals. Before we do that, we have to do something with those intervals. What do we want to do? Pick a number. Okay, so let's just worry about the pick a number business. So the first interval right here, -4, okay? Somebody give me a number for the next. -1, and the next?
1.
And the next?
4.
4, okay. I like 10 better, but that's good. So all you have to do right now is plug those numbers into f prime, and just tell me if you get a positive or negative result. So -4 into f prime. So you can just yell it out when you get it. Okay, -4 is positive.
-1 is negative.
1 is, okay.
So is 1.
1 is negative as well.
Yeah. 10 is positive.
Okay. You guys agree?
Yes.
Okay, cool. So now, this is the part that's probably going to annoy you a little as to how much detail you have to give here. But I'm going to say f is increasing on... Somebody want to grab that? Thank you, Mark. F is increasing... Well, how many intervals did we say? 2. So f is increasing on negative infinity to -3 and 3 to infinity, because, here, don't leave this part off, because f prime of x is greater than 0 on negative infinity to -3, and f prime of x is greater than 0 on 3 to infinity. So somewhat of a lengthy...
Why did we have to write that? Yeah, why did we write that?
Well, see, it is really, really redundant. Okay, but you're not going to be able to like do the whole... I made this decision because draw an arrow to
Oh, is this
your
like
previous work.
justifying it
This
for
is
on the AP test?
exactly. This is justifying it on the AP test.
But for you, do we have to do this?
Well, see, I want you to be in the habit of that so you can pick up all those points. Yeah, because the thing is, you're going to know it, and you're going to be so frustrated, not that you'll ever know. Like, it'd be really frustrating to, like, if you know all the calculus that you need to, but you're not able to present it in the way that they want it presented, that'll be frustrating for you and for me, and so... So yes, very redundant. That's how you need to make that statement. There's a couple ways to organize that statement, but if you ever want to say f is increasing, you better be able to say because and link it to some calculus. If you say f is increasing because the graph of f shows it, you know, if they could, they'd probably give you negative points, but they're not going to. And they're not going to give you any points there. So now we've got to make a statement on when f is decreasing. So f... And I'll write this statement a little bit differently, okay, just so you see another way to do it. I'm going to say f prime of x is less than 0 on negative 3 to 0. Therefore, f of x is decreasing on negative 3 to 0. Therefore,
Wait, isn't it? That's it's supposed to be 0 to 3.
oh, 0 to 3. Did I put the wrong one in there? So what were they? They were negative 3 to 0 and 0 to 3. Good job. Negative 3 to 0 and 0 to 3. Good catch. And you could write it in the reverse order, right? You could say f of x is decreasing on negative 3 to 0 because f prime of x is less than 0 on negative 3 to 0. But really, I mean, so you got f is increasing on this and this. The justification follows. That has to be there. F is decreasing on this. F is decreasing on this. So they've got to have the justifications. Now, if you like that justification, wait until we get to the relative extrema. So relative extrema is next. That's B. So relative extrema, let's see. We've got a relative extrema. I don't like these numbers sitting here. I'd rather have the intervals sitting in there. Something happens at negative 3, right? And you got a max or a min at negative 3? Max. Max. Because leading into negative 3, you're increasing. Coming out of negative 3, you're decreasing.
Okay, yeah.
So going up to going down. Now, that's not enough, right? You can't just say function increases, then decreases. You also need to say your function is defined there, right? Because you could have a discontinuity, and on either, and it certainly would go from increasing to decreasing. But your function also has to exist there for it to be a relative extreme value.
At 3, is there a local minimum?
At 3, there's a local min. Yep. So we'll have two things going on here. So we're going to say relative max at x equals 3 because f of, or sorry, it was negative 3, because f of negative 3 exists and f prime of x is greater than 0, negative infinity to negative 3, is less than 0 on negative 3 to 0. The part that students will leave off is like making sure to say, oh yeah, your function exists here. So we'll do the same thing, but we'll do it now for the relative min that you guys had identified. So if you got a minimum, do you go from decreasing to increasing or increasing to decreasing? Think about it real quick. If you formed a minimum, did you come in going down and go out going up, or is it the other way? Down to up, okay. So 0 to 3. Now, they don't ask us about absolute, so we really don't, although something funky happens at x equals 0, we don't really care that much, right? I mean, because it ultimately is a vertical asymptote, but a vertical asymptote isn't going to produce a relative maximum or a minimum. So, you know, when you got a vertical asymptote, you know, both sides of that vertical asymptote could go up, or they could go different directions, you know, thus affecting absolute extrema, but they don't ask us about absolute extrema, so we're not going to worry about it here. Any chance we have a relative extreme value at x equals 0? No, because 0 doesn't exist. Function's not defined there. Good. So then we go to C, which is a lot like A. Intervals of concavity is a lot like intervals of increasing and decreasing. So you guys previously mentioned for C you were going to need access to the second derivative, which is we're thinking here. The video isn't froze.
Negative 4.
Negative 4.
In parentheses, x squared minus 18. Over x to the 5th. Is that wrong?
No, it's not wrong.
Okay, cool.
I'm pretty sure that's right.
Good job. So the only way we're going to change concavity is if, well, a few things happen, right? So you can change concavity if your second derivative goes to what? Crosses the x-axis, meaning your second derivative would be 0. So things that I'm thinking about, kind of in the back of my head, I'm saying, okay, f double prime of x equals 0. Question, when does that happen? F double prime of x is undefined. Or even your function was undefined. So those really, I mean, when I think about the interval, you know, the separators you use for those, you know, concave up and concave down, those are the things that come to my mind. So I want to know, do any of those things happen? Well, I'll go to the last one. F is undefined. That happens when x equals what? 0. So when x equals 0, so that's going to be a number that you're going to use as a separator for those intervals. So f double prime of x is undefined. When does that happen? So look at f double prime. What would make it undefined?
Wait, is that
0. But 0 isn't in our scope anyways. So I'm going to say f double prime of x does not equal undefined on negative infinity to 0 union 0 to infinity. Or you could have said f double prime of x is not undefined on f's domain. So, but we're trying to tell them we're looking at it. And finally, where f double prime of x is 0.
Oh, is that
Plus or minus 1x, 1x equals plus or minus. Cool. And just for fun, you know, reducing radicals, any perfect squares in 18. Nine would be that perfect square. 9's there, 2's there. So square root of 18 reduces to 3 root 2. Okay. So we've located the only points where concavity could change. So we're going to write out our intervals. So the leftmost interval is from negative infinity to what? Okay. Next interval. Good. Next one. And 3 root 2 to infinity. Okay, I've got to provide detailed justifications once again. As I said here, I'll try to think of the shortest way to write it, but we want to be able to say when our function is concave up and concave down. So we better know real quick. So what's the next step in the process? Plug them in. Plug them into what? F prime prime, F double prime. So if you guys want to do that real quick, just pick a number in each interval, plug it into F prime prime.
Can you copy the derivative from here to
Yeah.
put it into...
Yeah, so highlight it and then I think the copy buttons. Highlight, like scroll up to it, like over it, and then So I'm actually going to pause this real quick while we're doing the calculator work. So we've got the signs on all those. Students just took numbers from all of these intervals, plugged them in, and then what you see here are the signs on those numbers after they were plugged into F double prime. So that's just going to tell us where F double prime is negative and positive and where your function is concave up and concave down. Yes. Anybody? You got a positive there. So what, Grayson? You mentioned you used -4, but -4 might not be between negative infinity and negative 3 root 2. So pick a bigger negative. So it is positive. Okay. Good check. So that's why, like, sometimes I'll just pick I'll pick -100.
Yeah.
You know, so I make sure I'm on the other side of it. Okay, so here we go. All I gotta do is justify. I gotta say when it's concave up and provide a justification. So F is concave up on, let's see, negative infinity, negative 3 root 2. Union 0, 3 root 2, because F double prime of x is greater than 0 on negative infinity to negative 3 root 2, union 0 to 3 root 2. Okay, one more. F is concave down. So while I write this, if you guys could be thinking about inflection points. Three root 2 to 0, union 3 root 2 to infinity, because F double prime of x is less than 0. So we've got those. The last part is D. The one tricky thing about inflection points when you can't see the graph is inflection points certainly do mean a change in concavity, but you've also got to be able to sketch the what? Sketch the tangent line. So like we're gonna say something here that's going to take care of that piece. If you can sketch the tangent line, is your function defined there?
No, not. Yeah.
But so even if it was this case like that, so you're saying that's a vertical tangent, is your function defined right there? But the slope's not. Okay, if I told you that somewhere, like at A, right? If I said, hey, by the way, at x equals A, f of A and f prime of A exist, would that be enough information for you to conclude that you could draw the tangent line there? Yeah. So still, I know if we came across the vertical tangent, it would give us trouble. But if those two things happen, we know we're not dealing with the vertical tangent thing. Okay, so here's how I'm going to get around this. So you guys are looking at that, and where do you think the first inflection point is? Negative 3 root 2. So watch this. So we're going to go inflection point. At, I should write probably at, I don't know, at x equals negative 3 root 2 because, now you'd want to go back and check this obviously, but watch how we're going to get around it. We're going to say because f of negative 3 root 2 exists, I know that because negative 3 root 2 is in the domain, and f prime of negative 3 root 2 exists. Also, f double prime of x is greater than 0 on, now I'm going to show what that concavity changes, so it's greater than 0 on negative infinity to negative 3 root 2, and f double prime of x is less than 0 on negative 3 root 2 to 0. I don't know if I picked that up. So that's how I creatively get around being able to draw the tangent. So, well, you know, the thing is I don't think I can check because you weren't even given f. You didn't start.
If you were given f, then you would have to check.
Yeah, exactly. If you were given f, you could graph it and check. But if you're not given f, you know, that's one good way to do it. So as you guys pack up, I'm just going to continue writing out because there is one more inflection point. Is that the positive? Is it 3 root 2? Oh, he's got it right there. F prime of 3 root 2 exist. Now we're going to show that the second derivative does cross the x-axis by showing to one side it's less than 0 and one side it's positive. So and f double prime of x, let's go back, it was greater than 0 and then less than 0. Greater than 0 on 0 to 3 root 2. And f double prime of x is less than 0 on 3 root 2 to infinity. Uh-oh, we gotta draw the infinity. I think we're gonna get this in time. We did it. All done. Good job, thank you. Good job, class. 29.